Morning, everyone. We're early, but I'm here because Delaney had some questions, so we could address those. We could address those before class. I don't know if she has arrived. Delaney? Let's wait. If you have questions while we're waiting? Anybody? No, we're good. Delaney, let me know when you get here. Perhaps you're here already. No. I don't know when the midterm is going to be. It's too early for that. If you go on WebWork, I don't know if you see it, but there's going to be a new assignment opening up on Monday. That's going to be on this stuff. Thank you. Yeah. How am I making it worse? P is asking if the tutorials are recorded. We will record one tutorial. I mean, there's really no point in recording all 14 or however many there are. We'll record one. But look, I mean, if you missed the tutorial you wanted to attend, just attend any other one. I mean, they're all the same, basically. I mean, the TAs are different, so the approach might be different, but yeah. WebWork is for marks, right? You understand that WebWork is for marks, except for WebWork 0, which was just a tutorial. I mean, the reason the TA doesn't share the solutions is because, you know, we want you to work through the questions yourself there. WebWorks have unlimited tries. It doesn't matter which tutorial you attend. There will be Monday tutorials starting next week, of course. The tutorials are not mandatory. Has Delaney arrived? Delaney, you had some questions. That's why we're here earlier. I won't be posting WebWork dates regularly. So, I mean, hi. So it's up to you to check. Delaney had some questions, so let's address those right now. I believe there are tutorials every day. First question is, what is an inverse? Right? And then let's discuss that. If you have a function right? Suppose you have some sort of function. I mean, we don't know. Just some function. I don't even want to write anything down here. But a function such that, let us say, f of 0 is 2. F of 1 is negative 1/2. F of 2 is 3. That kind of thing. Let's just say. The inverse, and here we're assuming the inverse exists, but the inverse is a function such that if you plug 2 in, you get the 0 back. If you plug negative 1/2 in, you get 1 back. If you plug 3 in, you get the 2 back. And now let's take a step back and understand what's happening here, right? You're plugging in some values of x, and you're getting some y value out of that. The inverse function is a function such that if you plug in that y value, you get the x back. That's the definition of the inverse function. And so what does that mean? What does that mean? The x values you're plugging in to your function, that's the domain of the function f. The y values you're getting out, that's the range of your function. So the domain of f is the x values. The range of f is that collection of y values you get out of that. Let's look at the inverse. The inverse, you're plugging in the y values. So the y values are the domain of f inverse. The range of f is the domain of f inverse. And similarly, the x values, here the x values are the range of f inverse, but it's the domain of f. So the domain of f is the range of f inverse. And there you go. So if we apply that to exponentials, if you have a function a to the x where a is bigger than 0, a is not equal to 1, we saw in that whole development that this function must have an inverse, right? I mean, the graph of this, if a is bigger than 1, this is the graph. And if a is less than 1, but still bigger than 0, this is the graph. In either case, by the horizontal line test, this function is 1 to 1. so it must have an inverse. Now, you know how to solve for the inverse, right? You would interchange x and y. So if y is a to the x, you would interchange x equals a to the y, and you would solve for y. But there is no way to solve for y. But we know the inverse exists. So we give it a name, and we call it the logarithm. The logarithm is the inverse of the exponential. People, I'm getting lots of questions about web work, due dates, and this and that. Everything is stated on web work. Log into web work. Don't ask when the web work is due and wait until that day to go. Log into web work right now and you'll see the due date. So that question isn't even necessary. Log into web work, and web work will tell you that information. So we have a function and its inverse. And as we saw in an earlier lecture, right? I mean, how do we solve for the inverse? We interchange x and y. So the graph of the inverse is going to be the graph with x and y interchanged. Right? In particular, if we look at this, the inverse, which is the logarithm, with base bigger than 1, right? Let's look at this. For large negative values of x, y is close to 0. So for large negative values of y, x is close to 0. That's the graph. That's the graph where a is bigger than 1. And for this one here, what are we saying? For large values of x, y is close to 0. So for large values of y, x is close to 0. And what's happening? As x goes to negative infinity, y goes to positive infinity. So as x goes to positive infinity, y goes to negative infinity. And there's the graph. This is for a between 0 and 1. Right? Once you know the graph of your function, you can find the graph of the inverse very easily. There it is. Somebody's asking for the graph of negative ln x. Let's do it. And I think Delaney, this answers the questions you had sent me. Now you were going to ask me some questions from the book, so you can do that right now, at least a few. We don't want to take up too much time, but at least a few questions. Somebody was asking for the graph of negative ln x. Let's do it. If you look at the graph of e to the x, you know the inverse is the logarithm. So you know that graph. This is the, I've just run it off now, but it's the exponential where the base is bigger than 1. So the graph of this is going to be exactly that. And you want negative of that. So what does that do? All the negative values suddenly become positive, and all the positive values suddenly become negative. There it is. It's just reflection above the x-axis. This is the graph of negative ln x. I still don't have the 8th edition. So if you could send me the actual question, I mean, just type out the question. What is it asking for? Solve something or graph this? That's what I'm looking for. Willem is asking for question 19 from page 64. I don't have the book with me. You want to write it out? I haven't posted office hours yet because I'm very busy with the beginning of semester business. But as soon as I'm done with the other stuff, I will post office hours. If you have questions, though, you can email me. We can always set up a Zoom meeting if necessary. But I will be posting regular office hours at some point. Tina is asking for the inverse of 1 minus e to the x over 1 plus e to the x. A very nice question. Let's do it. You know what to do. Well, then I'm getting a lot of questions about inverses. A lot of those are not necessarily possible to do, right? I mean, if you have an exponential and a polynomial, it's going to be difficult, if not impossible. Willem, though, is asking a different kind of question. Let's find the inverse of this, though, first. You know what to do. You're going to interchange x and y. And solve for y. So cross multiply. Expand. Bring this to the other side. And that over there. So you get x e to the y plus e to the y is equal to 1 minus x. Factor out an e to the y. So you get, and now isolate for e to the y, so divide. This is 1 minus x over 1 plus x. And now you want to get rid of the exponential. If you do the same thing to both sides, equality is maintained. So I like to take ln of both sides. Now exponentials and logarithms are inverse functions of each other. So this is just y. And there you have it. Let's consider Willem's question, which is nice and tricky, because and you know that might answer the few questions that came before him. The question is asking if g of x is 3 plus x plus e to the x, what is G inverse of 4? And you're thinking to yourself, well, I mean, I need to find the inverse, right? So if you try to find the inverse, you're going to interchange x and y. And I want to say that this is impossible to solve for y. Exponentials and polynomials, I mean, you want to stay away from that. I don't think it's going to be possible to solve. Theoretically, this function must have an inverse. You can show that it's one-to-one. It's not easy, but once we do more of the calculus, you'll see a nice way to solve, to show that it's one-to-one. But let's take it for granted right now. It is one-to-one, so it has an inverse, but you're not going to be able to solve for the inverse. But it doesn't matter. Here's the trick. Observe that if you plug in 0, what do you get? You get 3 plus 0 plus 1, which is 4. So the inverse function is a function such that if you plug 4 in, you get the 0 back, and you're done. There it is. So you didn't need to find the inverse. And Delaney, your question is very similar to this. So let me not answer it, and I'll let you try to work it out. It's that same kind of example. Willem tried to solve for 4 algebraically and it doesn't work. Exactly. Exactly. Danielle is asking for the difference between log and ln. Ln is log with base e. So are you supposed to guess? Well, I mean, it's not a guess. It's an observation. You cannot solve for that algebraically, Shamir. Nobody's expecting you to solve for that algebraically. The book is not expecting you to solve for that. All right, let's go back to logarithms we were doing last time. Delaney, if you have more questions, we'll address them at the end of class. I'll stay a few more. I'll stay a bit longer, and we can do some stuff there. Let's go back to what we were looking at. Logarithms. We are asked to solve for x here, and I think I have given you a flavor in that example we did for solving for the inverse function. Can't we say x equals 0 so that you get 0 plus e to the 0 is equal to 1? Absolutely. But this isn't algebraically, right? I mean, this is really just an observation. In the same way here that we observed by plugging in 0, you get 4. If you set this equal to 4 and you try to solve, it's not going to work. Here we're solving for x. We're solving for x and what? what I like to do is, in the same way, I'm pointing to what I've erased here, when we were solving for the exponential, where we took ln of both sides, what I like to do is raise both sides to the exponential. So if log is equal to 2, then 2 to the log is equal to 2 to the 2. And what's the point here? Exponentials and logarithms are inverse functions of each other. So these just cancel out, leaving you with x squared minus x plus 1 is equal to 4. Now, somebody had suggested that originally, and this is equivalent to rewriting the logarithmic equation in terms of an exponential one. So however you wish to see it, it's fine. But I like this raising business. You're doing the same to both sides, equality is maintained. And now you can just cancel out. Bring this to the other side. Factor. How does this factor? X minus 3. No, it does not factor this way. It does not factor like that at all. In fact, it does not factor. It does not factor. What are we going to do? Jonathan doesn't understand how log is canceled down. Remember that if f of x is a to the x, its inverse function is the logarithm. So that when you compose the two, thank you, quadratic function, quadratic equation, go ahead and work that out. So when you compose the two, you get x back. But the composition is a to the log base a of x, which is exactly what we have here. A to the log base a of x. It just gives you the x back. Quadratic equation for this, negative b plus or minus square root of b squared minus 4ac all over 2a. So 1 plus or minus root 21 over 2. There it is. How are we doing? Questions? Anyone? No? We're good? Why can't x be 2? Well, I mean, if x is 2, you get 4 minus 2 is 2, minus 5 is not 0. Let's try another one. Same question, we're asked to solve for x. You know what to do. Let's bring a 1 to the other side. So we get e to the 4x plus 1 is equal to 19. Now you want to get rid of the exponential. And we're going to do the same trick we did with the inverse function there. We're going to take ln of both sides. If you do the same to both sides, equality is maintained. And ln and exponential being inverse functions of each other, these cancel out, leaving you with just the 4x plus 1. So 4x is ln of 19 minus 1, and x is ln of 19 minus 1 over 4. There it is. Thank you. Jennifer, that's a good question. Let's do this one first, and we'll do yours after. You can leave the answer as is, right? There's absolutely no reason for you to use a calculator to get ln of 19 as a decimal value. Claire, we didn't actually have that. It's not 2 to the 4x plus 1, it's e. And e and ln are, well, e to the x and ln x are inverse functions of each other, so they cancel out. Let's cross multiply here. 1 plus e to the minus x is equal to 15. Right? So e to the minus x is equal to 14. And we're going to do the same thing again. We're going to take ln of both sides. Do the same to both sides. Equality is maintained. And again, exponentials and logarithms are inverse functions of each other. So this cancels, this left-hand side cancels to give you negative x. So x is negative ln of 14. Thank you, Matthew. Let's consider Jennifer's question. E to the ax is equal to c e to the bx. Solve for x. Whatever you want to do. There are several approaches. What do you want to do? Meaning that you can take ln of both sides. So ln of e to the ax is ln of c e to the bx. If you do the same thing to both sides, equality is maintained. Here, ln and exponentials are inverse functions of each other. So you just get ax. Here, you have ln of a product. So this is the sum of the logarithms, ln c plus ln e to the bx. And now, again, exponentials and logarithms are inverse functions of each other. So this cancels out, leaving you with the bx. Bring the bx to the other side. Factor out an x. And now you see why in the question it was stated that a is not equal to b. If a is not equal to b, this is not 0. So you can divide. And the answer is ln c over a minus b. Very nice. Very nice question. Right, in the beginning it wasn't clear why you didn't want a to be equal to b, but now you see. All right. Questions? So it's the same question. We're asked to solve for x. And let's understand what we're going to do here. You know the graph of ln of x. Matthew will do that question after. But it's the same thing we've been doing over and over again. Okay, let me start you off and take the exponential of both sides. But back to this. What are we saying? This is going to be something between 1 and 2. And look at your function ln of x. Ln of x, how would you describe that function? You would say that it's a function that keeps getting larger and larger. It's an increasing function. Right? So if you take a value that's bigger than 1, then ln of this value is going to be bigger than ln of that value. And similarly, ln of this value is going to be bigger than ln of that value. Your function is increasing. So when you take the logarithm, the inequality is maintained. So exactly as suggested, ln of 1, if you take ln of everything, equality is maintained. And what does that do? Exponentials and logarithms are inverse functions of each other. The stuff in the middle is just 3x minus 1. Now you know what ln of 1 is. Ln of 1 is 0. So we have 0 less than 3x minus 1 less than ln 2. Add 1 everywhere. Inequality will be maintained. right? If you add 1 to everywhere, inequality is maintained. And finally, multiply the whole equation by 1/3. 1/3 is bigger than 0, so inequality is maintained as well. You know that if you were multiplying by a number less than 0, the inequality would switch, right? But 1/3 is bigger than 0, so what do we get? 1/3 times 1, 1/3 times 3x, and there it is. Why are we multiplying by 1/3? We were asked to solve for x. So here you see that x has to live in this region. How are we doing? I think, what was it? Willem had a question earlier, or maybe it was somebody else. Matthew, ln of ln x. Solve for x, right? Same question. How do we go from here to there? Add 1 everywhere. Right? So we're starting off with this. We're going to do the same thing to both sides. We're going to raise both sides to the exponential. So e to that is equal to e to that. But exponentials and logarithms are inverse functions of each other. So this left-hand side is ln x. Right-hand side is 1. Repeat. And you get x is e. Let's do one more. Well, I'm raising this to the exponential. So I'm saying e to that is equal to e to that. B of which question? Yes, that's a 62. Will we do inverse trig functions today? I don't know if we'll get to that. We will certainly do trig functions though. That's our last example, and we're moving on to trig. Same question, we're asked to solve for x. And let's bring the 1 to the other side. And we get minus 2 ln x is less than 2. And now let's multiply the whole equation, or the whole inequality by -1/2. Now, when you multiply by a positive number, you know the inequality is maintained. And when you multiply by a negative number, you know that the inequality reverses. So now I'm multiplying by -1/2 to get rid of this -2, so that the left-hand side just becomes ln x, but this reverses the inequality. Everywhere. Everywhere. When do inequalities reverse? Well, exactly then. Let's convince ourselves. You know that 2 is less than or equal to 3. And if I multiply this by the number 4, what happens? I get 8 versus 12. Which one is bigger? Well, there you go. 12 is bigger than 8. The inequality has been maintained. However, if you start with 2 and 3 again, and you multiply by -2, both sides, what happens? This is -4, and this is -6. Which one is bigger? The -4 is bigger. So that's what happens. The inequality reverses. Why? Why is that? Does anybody have a good answer to that? I mean, it's clear algebraically that that's what's happening. But why? It has everything to do with what we were looking at before. In the previous questions, when we were solving inequalities, I said take ln of both sides, or ln of each piece, and equality is maintained. What happened there? Right? We said inequality is maintained because your ln function is an increasing function. So if you take two values, one that is less than or equal to the other, ln of A, so if A is less than B, then ln of A is going to be ln of B. Is going to be less than ln of B, right? Because you can see from the graph that your function is getting larger and larger. So smaller values yield smaller results. If you look at the line y equals mx, where m is positive, what does the graph of that look like? Well, it looks like this. Positive slope. And what can you say? This function is increasing. Right? If A is less than B, then very much like ln of A was less than ln of B, MA is going to be less than MB. But this is only true if m is positive. Because if m is negative, you know what the graph looks like. Negative slope means it's coming down. And once again, if A is less than B, here your function is decreasing. Right? So the smaller values give rise to the larger right? Smaller values give rise to larger y values. So MA is actually going to be bigger than MB. How are we doing? Questions? Let's finish that up. Did you guys finish it up? Take exponentials again. And we get x is bigger than e to the negative 1. Questions before we move away from this? Anyone? We're good? Moving on? Moving on to trigonometry. First of all, before we tackle trigonometry, which has everything to do with triangle and angles, as you know, let me point out that degrees are out. Radian measure. Degrees are out, radian measure is in. Shouldn't the sine be going the other way? We took exponentials, and you know the exponential is an increasing function, so exponential of a smaller value of a larger one gives rise to, so no, we're fine, we're fine. We're moving on from 1.5. This is going to be appendix D at the end of the book. We don't use degrees. Exactly. Exactly that. We don't use degrees, we must use radian measure. The reason for that is not immediately clear at this point. But it will be clear in about a month. And there's an excellent reason why you want to restrict your attention to radian measure as opposed to degrees. So first, let's discuss radian measure. What is radian measure? Suppose you have a circle. Of radius r. We're going to define one radian as the measure which gives an arc of length r. So that's how we're going to define one radian. This angle so that the arc has the same length as the radius. And observe that this, you know the circumference of a circle is 2 pi r. So in order for this measure to have a circumference of just r, right? It's only part of this arc length. In order for the arc length to be r here, it's really just a portion of the circle. What portion of the circle, right? So if if I multiply this whole thing, right? I mean, I want to get rid of the 2 pi. So if I multiply this whole thing by 1 over 2 pi, I get r. In other words, this has to be, 1 radian has to be this portion of the circle. And there it is. So the whole circle has to be 2 pi. Has to be 2 pi radians. But you know a full circle around is 360 degrees. Is 360 degrees. So 360 has to be 2 pi radians, or 1 degree has to be pi over 180. And this is how you can go from radians to degrees and vice versa. Consequently, 180 degrees, if you multiply both sides by 180, 180 in radian measure is pi. 90 degrees, if you divide this by 2, pi over 2. If you divide by 2 again, 45 degrees is pi over 4. If you divide this by 3, 60 degrees is pi over 3, and so on and so on. Now, trigonometry rests on the beautiful fact that if you have right-angled triangles with the same interior angles, the ratios of the sides remain the same. Kayla is asking if you're going to have to memorize the derivatives of cos, sine, and tan. Well, I mean, that's the least of our worries. Right, so ratio of the sides are always going to be the same in a right-angled triangle, which consequently, given an angle between 0 and pi over 2, we can look at the right-angled triangle with this angle theta here stated, and with respect to this angle, this we can label as the side opposite to the angle. This is going to be the side adjacent, and consequently, the long side is the hypotenuse. And from there, we can define the 6 trigonometric functions. Sine of theta, right? So again, the idea being that the ratio of two sides remains the same no matter which size triangle you take, as long as it has the same degree, the same angle. We're going to define sine as the ratio opposite over adjacent. We're going to define cosine as adjacent over hypotenuse. So, sorry, what did I say there? Opposite over hypotenuse. Adjacent over hypotenuse. Let us define tangent as the ratio of the side opposite over adjacent. We'll define cotangent as the ratio of adjacent over opposite. Let us define secant as hypotenuse over adjacent. And finally, cosecant as hypotenuse over opposite. Let's take a few examples. Let's take a few examples of important triangles. One important triangle is an equilateral triangle where all sides are equal. Now, this is not a right angle triangle, so this trig stuff does not apply to that immediately. But if all sides are equal, then all angles are equal. And you know that the sum of the interior angles of a triangle add up to, you know what they add up to, 180 degrees. Absolutely, thank you. And consequently, if the three angles are the same, they had to be 60 degrees to begin with. Now, let's split that right down the middle to form a right angle triangle. So if we do that, if this was 60 degrees, and we split that one right down the middle, then this one is 30 degrees. We have a side of 2 here. If we split it right down the middle, this is now side 1. And let's apply the Pythagorean Theorem to figure out what this side is. By the Pythagorean Theorem, 1 squared plus b squared is equal to 2 squared. And so it's easy to see that b is root 3, thank you. So there you go. This is root 3. Now, I mean, I've written these as degrees, but, you know, to be consistent, I told you degrees were out. So 60 degrees in radian measure is pi over 3, thank you. And 30 degrees is half of that, so pi over 6. 1, 2, root 3. And now let's use these to figure out sine, cosine, and all the trig angles for these values. Let's start with pi over 6. Sine of pi over 6. This is the side opposite. So sine of pi over 6. I'm sure you've committed this to memory already. Always around this time, right? 12:30, 12:40. It's crazy. I don't know what that is. Very good. Thank you, Michael. So, I mean, I've only done half of them. I'll let you work out the other half. Let us discuss sine of pi over 3. For pi over 3, this is the side opposite. This is the side adjacent. This is still the hypotenuse. Sine of pi over 3 is opposite over hypotenuse, root 3 over 2. Cosine of pi over 3 is adjacent over hypotenuse, 1/2. Tangent of pi over 3 is opposite over adjacent, root 3, and so on, and so on. If you have a tutorial, you want to go to the tutorial. It's not Fresca. Fresca is something different. Questions here? How are we doing? Again, I'll leave you to fill in the rest, the other 3. So that's one important triangle that you probably want to commit to memory. We're going to be using these values over and over. PM, don't worry about Fresca. I'll make an announcement. It's not really up and running so well yet. So you probably want to commit this to memory because we'll be using it over and over in this course and in 141 as well. One more. Consider a right angle triangle where both of these sides are 1. Since both of these sides are the same length, these two angles have to be the same. And since this is 90 degrees, this leaves 90 degrees for these two angles, or 45 degrees each. 45 degrees, or in radian measure, pi over 4. By the Pythagorean Theorem, this square plus this square is equal to that square. So it's easy to see that this hypotenuse is, you know what it is. Solve for it. 1 squared plus 1 squared is a hypotenuse squared. So hypotenuse is root 2, thank you. And consequently, sine of pi over 4, opposite over hypotenuse. Cosine of pi over 4, adjacent over hypotenuse. Tangent of pi over 4, opposite over adjacent, and so on, and so on. How are we doing here? Questions? So, I mean, what have we done? We have essentially defined sine, cos. In fact, the 6 trig functions for any angle bigger than 0 and less than 90 degrees. We have defined 6 new functions. On 0 to pi over 2. For any value between 0 and pi over 2, you can draw a right angle triangle with this angle right here. And you can define the values of those 6 trig functions. What we would like to do now is extend this domain to all real numbers. How can we extend to all real numbers? Well, observe that this definition here, if you place this right angle triangle on the xy plane with the angle theta measured counterclockwise from the positive x-axis, and since we're allowed to take any right angle triangle, let's in particular take a right angle triangle where the hypotenuse is 1. Observe that, what do we observe? If we call this, right, if we look at this point, xy, where this is x and this is y, right? Sine of that angle is opposite over hypotenuse. So it's y over 1. And cosine of that angle is x over 1. In other words, x is cos theta and y is sine theta. This point here is cos theta sine theta. But this point is where this line here that has angle theta intersects the circle of radius 1. So for any angle theta between 0 and pi over 2, our definition coincides with the intersection of this ray with the circle of radius 1. Cosine is just the x value, sine is the y. And in that fashion, we can extend sine and cosine to all real numbers. So we extend sine and cosine to r via this fashion. If you want to figure out what sine and cosine are for some other angle, measure your angle, look at the ray, and wherever this intersects, the x value is the cosine, the y value is the sine. That is always the case. This is how we're extending to all real numbers. Well, I mean, here this is going to extend for positive values. So if positive values are measured this way, namely counterclockwise, negative values are going to be measured the other way, clockwise. And that is why sine squared plus cosine squared is equal to 1. Exactly, right? Because you are living, this point xy lives on the circle of radius 1. Well, what is the equation of the circle of radius 1? It's x squared plus y squared equal to 1. But if x is cosine, then this is cosine squared plus sine squared is equal to 1. And there you go. Sine squared plus cosine squared is equal to 1 in all cases. We could have proven it directly from here using the Pythagorean theorem, right? Pythagorean theorem tells you that this squared plus this squared is equal to that squared. So adjacent squared plus opposite squared is equal to hypotenuse squared. And if you multiply the whole equation by 1 over hypotenuse squared, what do you get? You get adjacent over hypotenuse squared, opposite over hypotenuse squared is equal to 1, but this is cosine. And this is sine. Of course, this is only valid for angles between 0 and pi over 2, and then you could extend it by this observation as well. There it is. How are we doing here? Why don't we use this idea to ask ourselves, what is cosine of 3 pi over 4? What is sine of 3 pi over 4? Right, so we want to discuss the angle 3 pi over 4. So let's call it this. This is the angle 3 pi over 4. And let's look at the complementary angle, pi over 4, right? Because this angle here is really pi over 4. Because 3 pi over 4 plus pi over 4 is pi, which is 90 degrees. So the values of sine and cosine are going to be related to pi over 4. How so? Well, you know what cosine of pi over 4 and sine of pi over 4 actually are, right? Cosine of pi over 4 is 1 over root 2, and sine of pi over 4 is 1 over root 2. So this point right here is 1 over root 2, 1 over root 2. What is this point then going to be? Well, it's easy to see that the y value is the same. And the x value, right? I mean, this side has to be pi over 2. So this side has to be pi over 2. But you see that the x is negative here. So this is going to be the point negative 1 over root 2. 1 over root 2. So cosine, which is the x value, is negative 1 over root 2, whereas sine, the y value, positive. There it is. So this is the way that you can figure out all the values for sine, cosine, and the remaining 6 or remaining 4 trig functions for any value of r. We'll pick this up again on Monday. I've opened up a web work for you already on the pre-calculus material, if you will. Stuff we didn't really cover, but for which videos were uploaded. It's just to make sure that you're comfortable with that material. So have a look at that. A real, well, I mean, it's still real because it is for marks, but a second web work will open up on Monday with respect to exponentials, logarithms, and trig functions. So you have that to look forward to as well. Questions? So we'll pick this up again on Monday and see how far we get. You guys have a good weekend? They are all unlimited attempts, yes. I think Delaney had some questions. If some of you want to stick around, we'll answer those. You guys have a good one. I'll see you on Monday. I don't really care, Jordan, about rationalization. You can do it. It's fine. Either way. What sections are the practice problems in? I think we were still doing 1.5 earlier. Now we're moving on to trig that you'll find in Appendix D. The first 4 marks web work has been opened, yes. You will, I mean, as far as the assignments are concerned, it is only web work. Sine of 3 pi over 4. So first, figure out where 3 pi over 4 is, right? So 45 degrees, 90 degrees, or pi over 4, 2 pi over 4, 3 pi over 4. 3 pi over 4 is right in the middle here. This is 3 pi over 4. Right, so pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. 4 pi over 4 is just pi, which is 90 degrees, which is 180 degrees, sorry. So if this is 3 pi over 4, then this angle will be pi over 4. So you see what's happening, right? I mean, we have this right angle triangle here where that angle is pi over 4. But you've seen that before. You have that same one right here. So, of course, this triangle is the same as that one. And that length is going to be the same as this length. And that length is going to be the same as that length. But you know these values, right? We did them before. This is one of our special triangles. We saw that sine of pi over 4 is 1 over root 2. Cosine of pi over 4 is 1 over root 2. So cosine and sine, right, this point right here, this x and y point, is cosine and sine respectively. And that is 1 over root 2. 1 over root 2. Which means that this length, this x length, right, because that's a point xy, so this length is 1 over root 2. And this length, this y, is 1 over root 2. So over here, this length has to be the same, and that length has to be the same. So this length has to be 1 over root 2, and this length has to be 1 over root 2. But if the length is 1 over root 2, this point right here has to be negative 1 over root 2, because it's in the negative x region. So this point right here, this xy point, is cosine of 3 pi over 2, 3 pi over 4, and sine of 3 pi over 4. But this point, the x value is negative 1 over root 2, and the y value is 1 over root 2. So negative 1 over root 2 for the x, 1 over root 2 for the y. So cosine has to be this, and sine has to be that. Well, Grace is asking if exams are coming. It's always coming, right? You could write it as root 2 over 2, absolutely. Questions? Anybody? Delaney, very good. Let's do it. Just one midterm, one final. All the details are posted on my courses. That's what my courses says, right? In this syllabus. Just one midterm, one final. We haven't announced a date yet, but it's not like I'm going to surprise you with a midterm tomorrow. I will give you plenty of time once we've decided on a date. You should expect somewhere around the end of October or early November for the midterm. So Delaney was asking if f of x is x to the 5 plus x cubed plus x. Find f inverse of 3 All right. Now, of course, don't read too much into this. This is not actually asking you to solve for x, right? It's not actually asking you to solve for the inverse function. It's just asking you for a nice observation, namely, what happens if you plug 1 in? What's f of 1? And, it's not even asking you to show that this function has an inverse. It's not asking you to show that this function is 1 to 1. We'll see a nice way to do that eventually, but with the techniques we have so far, it's actually pretty hard to do. In fact, let me say it's impossible to do. But as you pointed out, f of 1 is 3. So the inverse function, if you plug 3 in, you should get 1 back, you're done. That's the answer. And then it's asking for f of f inverse of 2. But there's nothing to do here. Assuming, of course, all of these things are actually defined, which we have not checked. But you know what happens if we take the composition of a function and its inverse. What happens? If you take the composition of a function and its inverse, you get x back. If you take the composition of a function and its inverse, you get x back. F of f inverse of 2 is exactly that. That's it. Nothing to solve. It's just an understanding of what's going on. It's the understanding of what happens when you work with a function and its inverse. That's all it is. So, Delaney, you were asking about domain and range, and perhaps I wasn't as clear as I should have been. In fact, I never actually told you what the domain and range was for the logarithm. So why don't we take a moment to answer that? I mean, I'm sure you probably know it, but we never spelled it out. So y equals a to the x. So that's your function. F of x is a to the x. Here I'm assuming a to be bigger than 1. Let's restrict our attention to that. The other one is going to be the same anyways. So well, I mean, from the graphs you can tell what the domain and range are. What is the domain for this function? Domain is the x values you can plug in, and you see that you can plug in. What is the domain for the exponential function? Is anybody still here? Infinity, thank you. It's all real number. From negative infinity to infinity, the domain is all real numbers. What about the range? The range is the y values. What y values does it hit? Right? If you were to squish that to the y-axis, y bigger than 0. So the range is going to be values bigger than 0. Bring that forward to the inverse function. The domain of the inverse function is the range of the original function. So here the domain, without even looking at the graph, the domain is the range of the original function. So 0 to infinity, the range is the domain of the original function. And that makes perfect sense, right? This logarithm is only defined for values bigger than 0. There's nothing, there's no graph here. For values less than 0, there's no graph. It's only for values bigger than 0. And the range, if you were to squish this, I mean, it hits all the y values, right? If you were to project it onto the y-axis, you get all the values. There it is. How are we doing? Questions? We're good? Very good. So, you know, you can keep working on this. And if you've got questions, you can email me over the weekend. Otherwise, you guys have a good weekend. And I'll see you on Monday.